There we go. All right. All right. Without further ado, so this is joint work with Balázs Bárány in Budapest, and essentially this came out of a completely different project. But we stumbled upon this, so yeah, I'll try and talk you through this journey. All right. So maybe first just start by saying what this shrinking target problem is. So if you have some dynamical systems, maybe some invariant measure, some other quantity that you want to study, and you have a sequence of targets, some subsets of the space that maybe move through the space, or you just take a certain ball and you shrink this ball, or just take just a ball and don't do anything with it. You have this sequence of targets. And what you want to know is, well, you want to study the set of all points that hit these targets infinitely often. And because the target can move with every iteration, you have a lot more flexibility than having a certain fixed set or just a single target. Anyway, so this shrinking target problem is just this recurrence to this moving target, usually shrinking. And just to have a picture, well, this is roughly what's happening. You just have a certain number of sets, maybe they're balls, maybe they're ellipses or something else. And you take your point, you iterate it through the space in your dynamical system. And every now and then you hit the ball at the right time. So the Tn+1 iterate in here, for example, is in the n+1 ball. All the other ones are not in there. And right, and you look at this set and you want to just study its properties. So why would you want to study this? Well, there are many links to other disciplines. One of them is Diophantine approximation. I don't do anything with Diophantine approximation, so this is just maybe a glimpse of what else you could do. So well-proximal numbers, for example, you can express in terms of these shrinking targets, where you just take all these rational numbers and you have a ball around all of these rational numbers and you shrink all of these at the right rate. Then you get this well-approximable set that's maybe some reference function psi here, well-approximable. Anyway, so what we're interested in here is the size of these sets. And coming from the St. Andrews School of Fractal Geometry, really what we're interested in are dimensions. But generally, you might want to just do a sanity check. Well, what do you expect? Well, if you have these targets, and if they shrink very, very slowly or not at all, well, what would you expect? Well, you would expect a lot of points to go in there, almost all points or something. And if they shrink incredibly fast, well, you would hardly pick up any sets in there. So it's very unlikely for them to be in that correct set at the end iteration. So to make it a bit more formal, what do we want with size? Well, you could think of the invariant measure and see what happens to this measure. And quite often you get these 0-1 laws, like Borel-Cantelli type laws. But even if you have these very fast shrinking ones, these recurrent sets may also not be empty. So usually it's very hand wavy here, they are dense in your phase space. So just looking at this as a topological thing, just okay, denseness you can get, it's uncountable. So from my perspective, oh, what do? I throw dimensions at it and see how big the set is in terms of dimension theory. And just to remind you, the Hausdorff dimension, it's just a number, but this number encapsulates how well you can cover a set. So you take your set and you cover it with some other countable set, and you look at the diameters to the power s, and you see what's the critical exponent s for which it becomes incredibly easy to cover something. And this exponent s here, this is the Hausdorff dimension of your set. All right, so go a bit into the history. So Hill and Villani were the first ones to really study this problem in this kind of setting. First with the Hausdorff dimension, then with the Hausdorff measure. And they did this for Julia set, as it says here, but many other people have since then expanded the work on these shrinking target type problems. And I'm sure I've missed out some of these names. Please don't feel insulted if you've worked on them. But this is kind of some of the literature that's available. But most of these really were considering either one-dimensional dynamical systems or conformal or nicely behaved dynamical systems. And in this talk, what I really want to talk about is the go-to example for something non-conformal from my point of view, so something self-affine. And for those, much less is known. So Hannah, Koivusalo, and Ramirez, they studied typical self-affine sets, much the same way that we want to do it. But also Balázs Bárány and Michael Rams did this for bedrock Malin carpets. I'll get to them in a minute. And another one is Simon Baker, who studied a bit more from a number theoretical perspective. But these are really the only ones, the only major ones that study this in the affine setting, the self-affine setting. All right, so what's a self-affine set? Well, so a self-affine set is an invariant set under some dynamical systems, under some maps. And what you do is, well, you take a finite number of maps and you take a bunch of matrices, non-singular, D by D matrices with dimension D. They might have to satisfy some norm conditions so that they contract enough. And you take some translation vectors and you have functions, a finite number of functions that are of this form. So you have, you take a point, you multiply this by this matrix, and you translate it somewhere in the space. And it's a classical result, Hutchison, that, well, there exists a unique non-empty compact invariant set out of those. It satisfies this equation, and this is known as the self-affine set if all of these maps were affine maps. And using this collection of maps we refer to as the iterative function system. And well, just as an aside, and we'll be talking about this briefly, if you take very regular functions, similarities, so that in this case, they would just be some orthogonal matrix with some real number that shrinks it down. So I should have said that C is less than 1, strictly between 0 and 1. Sorry about that. So this invariant set would be a self-similar set. So very nice and regular. All the images or all the parts of the set really are a similar copy of the entire set. Whereas for self-affine set, the small parts of the set are affine, so skewed parts of the entire set. Or if you want, you can think of it as this. You take your full shift, and you take the full alphabet, and you project this alphabet down into some geometric meaning with a projection that is, as I say here, you take some initial point, that doesn't really matter, 0, and then you iterate these functions according to the coding that you have, and the limit that you get there, that's the point. And a natural dynamic to look at then from the shrinking target problem perspective would be to do a shift, as in you look at this function, which essentially gets rid of the first symbol, the last map that you've applied to this point. Okay, so having set this up, some background. So this is all quite classical, but so the Hausdorff dimension, well, it encapsulates this shrinking behavior. And just to introduce self-affine, or before going to self-affine, I just want to talk about self-similar, just have an analogy. And the Hausdorff dimension and box counting dimension, all these other nicely behaved dimensions, they all coincide with this value here under mild, very mild assumptions. And well, the reason really, or you can at least see why this is an upper bound. Oh, well, I'll go to that. Oh, I say here it's typically, it's that way. Well, typically in many settings, actually, a big open problem is to see when it's not this value. But if you have these sufficiently disjoint copies, well, if you don't have too many overlaps, then this is the dimension. And to see it's an upper bound is also pretty straightforward. We want to cover something efficiently. That's what the Hausdorff dimension encapsulates. So why don't we just cover it with the images of our compact set? What are the diameters? Well, these diameters to the power s, well, we can just rearrange this slightly and you get this sum in there. And this sum is just the same sum that you had in the original condition. And this is going to be 1 if for this right exponent. And it's going to be less than 1 for anything bigger. So in particular, this means that if you have some exponent that is larger than this S0, this unique value, then this upper bound will go to 0. And that's exactly what the Hausdorff dimension encapsulates. This is the right bound. But for self-similar, it's quite easy because, well, you just take the set and you scale it down. Maybe you rotate it a bit or flip it around a bit. But for self-affine sets, it becomes more complicated because you have just a general matrix. So it can skew in different directions. You have different singular values of it. And this singular value function tries to encapsulate what is the best way of covering it, depending on your exponent. I don't expect you to remember this if you haven't seen this before, but there is a formula for it. But I'll, in a minute, I'll try to explain it more in 2 dimensions where it maybe is a bit more obvious what is happening. But what you do with this singular value function, it measures, in a way, the best way of covering your self-affine set. And if you plug this into this pressure-like formula, well, you just sum over all the words and you take the usual limiting process. Well, this pressure, also the zero of this, gives you the right exponent. It tells you the Hausdorff dimension of it. And the main result, or the first major result, was Falconer in '88, who proved that this is typically the case. So typically, this unique zero will give you the Hausdorff dimension of the set. It's always an upper bound. And it also coincides with, for example, the box counting dimension, other nice dimensions. All right, so how do we see that? Well, here is a bit of a drawing. So this singular value function wants to encode, well, what is the best way of covering it? And for these natural covers, then you just take originally like a big ball that captures the entire set. You scale it down with these maps and you get ellipses or ellipsoids on higher dimensions. And there are only a couple of ways of intuitive ways of covering it. And the first one would be just chuck a big ball that encapsulates this entire ellipse. So in particular, if this S in this singular value function is less than 1, well, it is the most efficient way of covering this bit of the set really is, oh yeah, great. Is just this first bit. And this is just what the singular value function tells you to take. And what it is, well, you take the major axis of this ellipse and you take this to the power S. That's how you cover it with this one ball of this size. But if you have a higher value of S, then maybe a different way of covering this is better. And this way is, well, you take this minor axis and you want to cover it with sets of the minor axis. How many do you need? Well, you need the major axis divided by the minor one. And that's exactly what's happening here. So for S greater than 1 in 2-dimensional space, we cover with this many balls, roughly, floor, ceiling, and you cover them with balls of this size. So the singular value function really gives you this. This is this divided by that, which is the -1 here. This gives you the number of balls and what size are they? Well, they're of size A2 second singular value to the power S. And the singular value function just does this in all dimensions. That's really what it does there. All right, so having defined this, knowing how to go about them, let me also show you where it doesn't work. So for self-similar sets, overlaps cause a lot of difficulty, and that's also part of the main conjectures in field, the dimension drop conjecture. Really about understanding how much these images overlap. You have different functions, they can overlap. What is the exact overlap? How can you quantify it, and how does it relate to the dimension? For self-affine sets, because we are skewing differently in different directions, also what we'll get is geometry coming in there, and this geometry is sometimes biting us and not wanting us to do this. So for example, if something is very highly aligned, like in this example, which is a representation of you take the unit square and you map the unit square into these rectangles. These are not similarities. One side is skewed by a third, the other one by a fifth. And you continue iterating this, you will get something which is heavily skewed. All these ellipses, these rectangles become very elongated in one direction. And for this highly aligned structure, things go wrong, seriously wrong. And generically, these do not no longer satisfy this generic equation. If you just take these specific subset of sets or subclass of sets, you will get different results. And so for the shrinking target problem, Balázs Bárány and Michael Rams, they investigate the problem just taking these mountain carpets and looking at either cylindrical targets, which are the dynamical way of looking at them, or geometric balls as targets, and see what happens. And this is quite an intricate picture, and I'm not going to summarize the result. It highly depends on the structure. How much do you skew it? And you get several different formulas. So it's quite complex. But for the generic version, Hannah, Koivusalo, and Ramirez, they looked at this classical setting, so the Faulkner setting, where you just take some affine functions, these matrices maybe satisfy some nice conditions, and you randomize the translation. And for almost every translation, you get this Faulkner function, this Faulkner result, this affine dimension bound. Okay, so what are the assumptions exactly? Well, they looked at just simple targets that are cylinders, and you have a fixed center. So you take an infinite word and you shrink it down. You look at longer and longer words of these. They also assumed, no, there we go. They also assumed this quasi-multiplicity condition, which is quite a strong condition on the matrices that you can actually kind of separate them out. And further, they also assumed that this modified pressure exists. So this normal pressure, but you also chuck in these words that you want, these targets. And then they get the result, what you would maybe expect. So the zero of this modified pressure function gives you the Hausdorff dimension of the recurrent set under these assumptions. And in short, what we did was relax it. So relax all of these assumptions to some extent, as much as we could. So we still stayed with cylinder targets, but arbitrary cylinders, but just arbitrary single cylinders, no collections of them. And we introduced this new measure here, which essentially just tells you how fast is the singular value shrinking for these words. And has some nice properties, monotone increasing, uniquely intersecting this pressure, and this intersection between the two is what we find is this Hausdorff dimension. Well, that's the result in short. So if you have some d by d matrices and some conditions, technical, with some nice shrinking of these the norm, then no matter what sequence of targets you pick in the symbolic space, the Hausdorff dimension is, for the back, almost every translation, a collection of translation vectors given by this intersection of these two. All right, so maybe in a bit more detail, but what are these conditions? So we say we need fully strongly irreducible and fully proximal. I'm not going to go much into it, but what they give us is this condition. It is some kind of quasi-multiplicity. Is that, well, whenever we have two matrices with some words, so these are just the products of all the matrices according to the word V, and this other matrix, we can always chuck in a word which has a fixed length, K, such that we get this lower bound. The upper bound, of course, is always given. And this is a modification of a result by Feng, which also arises from a natural condition on the matrices, where there's a uniform bound on this length, but we specifically need this to be one length, exactly. And in fact, if you have this condition, strictly just this condition by Feng, then it does not work. We do need this one fixed length. Okay, and well, you get this condition if you assume this fully proximal, distinct eigenvalue, and fully strongly irreducible, kind of a slightly stronger version of strongly irreducible, which I'm not going to go into because you need a lot of linear algebra to actually explain, but it essentially means that for all, not just the strong irreducibility, but the same holds for all kind of subsystems that you can have, not just for the system itself. Anyway, I'll gloss over that. So what does this proof involve? Well, the first is just that this technical condition of the matrices implies this other technical condition we actually use. That we have this one word where we can just inject a word and then we can split up the norm. And actually determining the dimension. The first is a modification, lots of linear algebra. I'm not gonna do this on a full stomach. So I'm just gonna talk about the dimension theory argument. And I'm also not going to give you full details, but if you've never seen this self-affine arguments before, this might be a nice introduction to the general theory behind it. Okay, so what do we do? Well, first of all, I'm just going to recall some basic inequalities. So these should just, well, they clearly arrive just from the properties that we had. So this pressure, well, it is related to sums over the singular value function, and you want this to, and this decays like the pressure, happening. So you get these bounds for large enough k, and also because it's the lim_inf, well, you get also this bound here. And because it's the lim_inf, you can pick a subsequence, and for this specific subsequence, you will also attain it. So you get this lower bound there as well. Okay, so what do we want? Well, it's a recurrent set. So what kind of set is it? Well, we can cover it by taking a large enough ball that encompasses the entire set, and then we map it down. We map it down by all of these words of length k, and we always just chuck in the target. So, well, these are all the things that hit the target at step k. These are all the ones that hit it from k naught, and then we take the intersection of all of it. That gives us this limsup set, which is a cover of it. So if we want to determine the Hausdorff dimension, well, here's a cover. Let's see whether it's a good cover, at least. What Hausdorff dimension does this cover predict? Well, what sizes are they? Well, you can show that they are of this size. So this is a cover. Once we just had the singular value function tells you how many there are and what size they are. So this value here gives you an upper bound of this dimension. Also encoding kind of how you split it up. But more than that, oh, sorry. So there should be a constant in here. So as I said, I'm glossing over a few things. So there's a ball, but you need to have you need to have the ball large enough to actually cover it all. So I'm going to ignore constants essentially. All right. So you use submultiplicativity. You can split this up, and then you get this nice thing. Well, how do these behave? Well, this is the same thing for all of them. This behaves like this alpha pressure that we had at some point. And what stays is just this, which is just the singular value function pressure for the normal unadulterated system. So what do you get? Well, you get this kind of bound, and just by how we picked everything works out nicely, and yay, we end up with an upper bound that is as small as we like. And this tells us that the Hausdorff dimension is smaller than or equal to this S, which we've picked to be greater than our target value, this S naught. Hence, it's an upper bound. Okay, so that's pretty standard, and it's just a basic covering argument. Now for the lower bound, what we are doing is taking also standard method. So this was not the original one, but this came a bit later on. And it's an energy type argument. So all we need to find is a good measure that lives on our space. And if this measure satisfies this condition, as in the energy with respect to this measure is finite, then it magically tells us that the set that it's supported on F has Hausdorff dimension bounded below by S. Okay, so, well, how does that give us something for the random systems? Well, the insight here is just to use Fubini, because, well, all we're going to do is we're going to take the system and take it over our parameter space of all translations. So if we now take the expectation essentially with respect to all of these translations, we can use Fubini, at least after rearranging all of these because they depend on the translation. You can use some clever tricks, you can rearrange it. And if you can show that this is finite, well, if this is finite, then almost surely, as in for almost every one of these translations, we have finite energy giving us the bound. Okay, so that's nice. So this looks more tangible, and even more tangible because of all the past history in this problem. We really only need to show this. We just need to focus on the parameter, on the symbolic space. We just need to show that there exists a measure on the symbolic space for which this holds. As in, instead of taking the distance, we take the singular value function. The singular value function really represents this distance here. Okay, so what do we do? Well, this is the wish list. Well, if we had quasi-multiplicity, well, we can just create a nice measure that sits on all of these individual words, and we can split them all up in a nice way. And we want something like this. So we want some word, some general word, and then chuck in very rarely these targets that we want to hit, and very sparsely hit these targets, and then take another one of these generic words, build up a measure that lives on exactly these, and we can use some multiplicity. So quasi-multiplicity perhaps to break it up into these little chunks. All of them behave nicely. We take this natural measure that lives on them, Kanmaki measure, and well, as I say, a short calculation gives you the result. And that's essentially what Koivusalo and Ramirez did. They used this assumption of quasi-multiplicity. Well, you get some constants in there, but these constants don't really matter. They wash out. But yeah, this does not hold in general. So, why is it going back? There we go. So what we do need to do is break it up into other blocks. And we also want, well, what we have is this condition that we can always inject this word of a fixed length to break things up and get this multiplicity constant. What we're doing is now breaking everything, even these three words, up into chunks of a certain length, p, say, and include these buffer words in between that we know are of length k. And with these buffer words, we can use multiplicity, this quasi-multiplicity. But it's a slightly more trickier to actually work out. So what you end up doing is modifying everything so that these lengths are always of a predictable length, in that you can always have these nice splits and you can work with measures that are just supported on these free symbols with some fixed symbols in between. The big problem really occurs in that this condition that we have, or also the Fang condition, the word that you inject depends not only on what came before, but also what comes behind it. So it depends on both of these words. You have to be slightly clever about how you actually inject these words. All right, so then you take some words, they're of this form, they're of a certain predictable length. And then on these nice words, you just chuck in the normal standard, nicely behaved Kanmaki measure. And the other ones are just a Dirac mass sitting on exactly these symbols. So the trick comes in actually working out the details of this. So, well, here's the kind of the idea behind all of this. So what you end up doing is rewriting this integral, and this is all pretty standard. So what you're doing is just, well, what is this? This is really nothing else than this summation. You take all of these blocks of words, you take your measure squared, and because we can use this condition with this join, the shortest answer of both, well, you get the same expression here. So really, you can just try to work out this expression here. And heuristically, well, this thing here looks kind of like this. This is the Kanmaki measure. It is just the normalized singular value. So you take the singular value function of this letter and it's normalized over all of these, roughly. And you do a bit of short calculation. Some things cancel each other somewhat, or you take some exponents. That's great. You get some upper bound of this. These two things cancels out the square. Great. Oh, no. How do I continue forward? There you go. And you get what you expect. As in, you get that these two things compete. You have this pressure greater than this lower pressure for exactly those words. And this converges. Of course, this is the very, very simplified version of this. Because you're always injecting these words, you always inject another constant in there. And this constant has to be finely controlled to actually show this as an upper bound. And really what also is quite tricky is to, well, we first worked with this Fang condition. We first wanted to show that this that it is just fine to inject some word, but this is not the case. So really what you're doing then is, if you just inject some words, well, you change the length of the string. Okay, maybe that doesn't sound too terrible. You just take some kind of, you have only finitely many choices. You take the one where this is the worst, where you get the most of the singular value function. So that seems to work out fine, but then you realize, actually, this doesn't work because, well, if you don't have fixed lengths, there might be cylinders, these targets that you have, that cannot ever be reached. Because whenever you want to target at a certain point k, well, if you need to inject a word in between. But injecting this word is not guaranteed to be the length that you want it to be. It could be a bit longer or a bit shorter, thereby not hitting that cylinder. So the upshot of this is, well, oh, no. I'll take a little while. Where's the result that we had? There we go. So the upshot of this is that this is in some way optimal in that we can't reduce the condition because that would allow certain words where these targets can never be reached. You can get around this, of course. You could rephrase this and say, well, we only take a fixed cylinder, a fixed target, and then it's fine as long as you don't change the length of the word too much. Or you can say, well, all of these targets, the singular value shouldn't change too much from function to function, but this is kind of cheating. I mean, this is just having this one target, that's fine. Maybe as a further kind of addendum, you could also just, instead of one target, you could take finitely many targets. Works out fine too, but once you get into some positive proportion of them, you get into trouble. So this is really the most that you can do there. Right, so the title, I also promised recurrence, and I haven't written much in here. So what we realized kind of as we wanted to put this in archive a while ago, but we also realized, well, our methods also, the cylinders that we are looking at, we could make them point dependent. As in this cylinder, this target here, we could also make dependent on the point that we're actually looking at. So giving us a bona fide recurrence problem, but yeah, we're still working on this. It's not quite worked out yet. So yeah, I will leave you with this image here for everyone who isn't here. And thank you for your attention.
Thank you so much for the talk. Are there any questions?
Can I see the Heno result?
Our result?
Heno and the Ramirez.
Heno, yes. Ooh, it will take a while, but I can already ask a question if you want, but there we go. It's a 0.
And the dimension of the matrix is the D or 2? What is the dimension of the matrix in this result?
D. They could be of any size.
Okay, in the dimension of the 2, your result doesn't follow from of the Heno and Ramirez because you assume the strongly irreducibility and fully proximal. Yeah. Bárány, Rams, Jordan, and Kermaki, they prove that for the under this assumption you have a dominated subsystem.
Right. No, yes. So this result specifically does not have it as a corollary. Yes, but once you have multiplicity, you can use the same argument to prove it as well.
No, but I'm just saying that when you assume that strongly irreducibility and fully proximal, they prove that we have a dominated subsystem, and that they show that the topological pressure of this dominated is equal to the whole topological pressure. And by using of this technique, they could calculate some upper bound of the some Hausdorff dimension. I'm saying of this thing because what's the Heno and Ramirez assume that they assume that almost additive, a mistaken assumption. But when you have a dominated subsystem in dimension 2 implies that almost additive, yes, which is the second assumption of the Heno.
So I don't see the problem.
But I'm just saying that your assumption in the dimension 2 imply that, I mean, approximately second assumption of the Heno and Ramirez.
Yes. Yes, so I don't see the problem right now.
But you say that you improve that this result. I don't understand these things.
This is, yeah, exactly. This is only in dimension 2. We do it for all dimensions. Yeah. Right, you mean, so the strong irreducibility in R2, this is
saying that in the dimension 2, I mean, your result.
Dimension 2, it's the same result. Yes, yeah. That's true, but also they make this assumption for all dimensions. So in dimension 2 specifically, yes, it's the same. We get the same. That's right.
Are there any other questions or comments? If not, let us thank the speaker again. And I think we're going to stay on schedule, and our next talk starts at 4 o'clock.